So let me read the problem. When a body moves in a circular path, no work is done by the force, since there is no displacement, there is no force, force and displacement are perpendicular to each other and force is always from the center. When a particle is undergoing a circular motion, the compulsory force is a centripetal force which is always directed towards the center. So, if you now consider this circular motion that he is talking about to be a uniform circular motion, when the speed of the particle will remain constant, then the only force which will be acting on the particle will be centripetal and directed towards the center. Okay. How does the particle get displaced while it is moving in a circular path? Always along the tangent drawn to the circle. So, if you look at the way the force is acting and the displacement is happening, displacement is along the tangent, force is along the radius, and radius and tangent are perpendicular to each other. So, angle is 90. Therefore, the work done by this force, that is centripetal force, is going to be 0. So, do not feel that only because the particle has undergone a complete circle, so it has reached the starting point, therefore the displacement is 0, therefore the work done is 0. Do not be under this impression, because even if the particle undergoes a very small displacement, say even a quarter circle or half a circle, still the work done by the centripetal force is going to be 0, because always the force and the displacement have remained perpendicular to each other. Therefore, the work done by the centripetal force in a complete circle, the work done by the centripetal force in a quarter circle, in a semicircle, in only a part of a circle also, the work done is 0. But if the motion were to be non-uniform circular motion, when there will be a tangential force also leading to the change in the speed of the particle in the circular motion, then the work done by this tangential force is not going to be 0, please remember, right. So, we will accept that the circular motion which has been given here is uniform circular motion, and the only force which is acting on the particle is centripetal, and the work done by that force is 0, and not because of any other reason that he has given here, but because of force and displacement being perpendicular to each other. So, this is the correct answer. There is no displacement is wrong, because I told you even if it is a quarter circle or a part of a circle also, the answer is going to be this. So, there can be a displacement. There is no force is ruled out, because if there were to be no force, why should the particle undergo a circular motion? Fine. Okay. And then force is always from the center? No, it is always directed towards the center. Fine. So, correct answer is C. So, this is similar to the previous problem. In the previous problem also, you were talking about the work done by the force acting on the particle undergoing a circular motion. So, let me read it here. The work done in carrying a charge small q once round a circle of radius capital R with charge capital Q at its center is. So, there is a charge capital Q which is at the center of a circle of radius R, and another charge small q is being taken round the circle. So, the work done is going to be 0 here, no doubt, but do not be under the impression that it is 0 only because you have gone round a complete circle and the displacement has become 0, because even if you had gone only a quarter circle or a semicircle also, the answer would have been 0. So, what exactly is the reason? The force which is acting on the charged particle is going to be along the line joining the two charges. Capital Q is at the center, small q is being taken round the circle. So, if you are talking about the work done by the electrostatic force, then that will be a force which will be along the radius and repulsive, and the displacement as you continue to take the particle along the circle will always going to be tangential. So, force is radial, displacement is tangential, angle between them is 90, cos 90 is 0. Therefore, the work done by the electrostatic force, see, unfortunately he has not made that particular point clear here, he only speaks about the work done in carrying a charge, right, but work done by whom is not known. So, let us just assume that he must be referring to the work done by the electrostatic force, right. So, if you are carrying the charge, then the work done by you is not going to be 0, because you may be always applying the force tangentially and you will be also making the displacement happen tangentially, right. But by the electrostatic force, which is radial, is always going to be 0, and whether you take it once round the circle or only a quarter circle or a part of a circle, work done is going to be 0. So, the answer is D. See, the problem goes like this. There is a truck which accelerates from a speed v to 2v, and the work done by whatever force which is acting on the truck and is responsible for changing its speed from v to 2v is. So, you have to select one among these options, and in all the options he has simply compared the work done by the force acting on the truck with works done, different works done. So, what we will do here is we will use work energy theorem. And let me again remind you that work energy theorem says work done by all the forces acting on a particle should be equal to change in kinetic energy of the particle. So, here we will consider the truck to be a particle. You have told us by how much has the kinetic energy of the truck changed. So, we will write down the work done on the truck by the force, right. So, how much is the change in the kinetic energy? Let us consider the mass of the truck to be m, and change in the kinetic energy is half m 2v whole square minus half m v square. So, now let me write down how much is the work done on the truck by simply writing its change in the kinetic energy. So, that will be half, say m is the mass of the truck, and v square. So, final velocity minus initial velocity. So, 2v whole square will be 4v square minus v square will be 3v square. So, 3 mv square by 2 is basically the work done by whatever force on the truck in accelerating it from v to 2v. Now, similarly, I will write the works done in all these 4 cases and pick up the right option. Okay. What will be the work done here? In accelerating it means accelerating the truck only. So, I will take the mass of the truck again from rest to v. So, initial kinetic energy is 0, final kinetic energy is going to be half m v square. So, half m v square will be the change in the kinetic energy or work done on the truck. 3 times of that makes it 3 into half m v square. 3 into half m v square. So, the first option is perfectly correct, but still we will read out the remaining options also, which will be an opportunity for you to know how to write the works done. Second option, same as the work done in accelerating it from rest to v. So, if you accelerate that truck, half m from rest to v means half m v square. So, half m v square will be the work done in the second option, but that is certainly not equal to 3 by 2 m v square. So, second option is wrong. Now, third option, 4 times the work done in accelerating it from rest to v. The work done in accelerating the truck from rest to v is half m v square, and 4 times of that makes it 2 m v square. And again, work done on the truck is also not equal to 2 m v square. So, C option is also wrong. Less than the work done in accelerating it from rest to v, it is less than half m v square, that is also wrong, because the actual work done is more than half m v square, it is 3 times. Now, that makes the first option perfectly correct, because the work done on the truck is this much, and the first option says 3 times the work done in accelerating the particle, that truck, from rest to v. So, half mv square into 3 makes it exactly 3 by 2 mv square. So, the first option is the right option. So, now another problem on work energy power. So, let us read it. An engine pumps water continuously through a hose with a velocity v, and m is the mass per unit length of water jet. What is the rate at which kinetic energy is imparted to water? So, rate at which kinetic energy is imparted to water means the change in the kinetic energy that water has suffered in the course of coming out of the hose per unit time. So, let us take 1 second time interval and try to calculate how much kinetic energy is imparted to the water. So, if I consider 1 second, then the amount of water which is going to come out is going to be the water which was present in the pipe with a length v into 1. See, because if you just permit 1 second, then how much water is going to come out? The water which was present in the pipe of length v into 1. Fine. So, v into 1 is the length of the pipe in which there is some amount of water, and all this water is going to come out within 1 second. Fine. Okay. Now, what is the mass per unit length of the water? Mass per unit length is m. So, if I multiply by m, I will get the total mass of the water which is going to come out of the hose within 1 second. What is the velocity with which the water is going to come out? V. So, I can write the kinetic energy of the water in 1 second. So, kinetic energy will be half m v square. So, this is half m into v square. So, that is going to be half m v cube. So, half m v cube will be the amount of kinetic energy associated with the water in 1 second. So, that makes the right option D. So, here is one more problem on power. See, there is a car of mass m which starts from rest and accelerates, which means it keeps on picking up the velocity, so that the instantaneous power delivered to the car has a constant magnitude and equal to p. So, the power which is being delivered to the car, because of which it is accelerating and picking up velocity and all that, is constant. So, we are not going to change the power. The instantaneous velocity of the car is proportional to. So, how does the velocity of the car depend on the time, or you can say depend on power, is the question. So, what we will do here is we will write what we know about power. I hope you all remember that power is F dot V, instantaneous power especially, and if you speak about the average power, it is rate of doing work, or you can say energy by time, or work done divided by time taken, right. But do not forget that here the car is accelerating, and because of which its velocity will continuously keep on changing, and therefore, you have to use the formula P is equal to F dot V. Actually speaking, it is F dot V, right, but do not forget that it is because of the force that the car is accelerating, and moreover it has started from rest. Therefore, the force and the velocity are both in the same direction, and hence I have written only F into V, because the angle between F and V is 0 and cos 0 is 1. So, P is F dot V actually, but I have written F into V because the car has started from rest, and it is because of the force that the car has accelerated. Therefore, the force and the velocity should be in the same direction, hence angle is 0 and cos 0 is 1, therefore, the dot product has simply reduced to F into V. So, this is the power. Now, I will write this as, this is constant. So, I will write F as mass into acceleration, and I am writing acceleration as dV by dt into V, and even acceleration and velocity are in the same direction. So, this has reduced to m dV by dt into V, and this is constant. So, we will take it as some constant k, the power is constant. Now, I will just cross multiply and solve the differential equation in order to find out the instantaneous velocity and its dependence on either p or time. So, what we get is mv dv is equal to k into dt. So, mv dv is equal to k into dt, or if you integrate from 0 to v, it is mv square by 2 is equal to kt. So, that makes velocity square proportional to time, or v proportional to t raised to half. Fine. So, the correct option here is C. V is proportional to t raised to half. So, we wrote power, we just expressed the force as mass into acceleration, power was given to be constant, we separated the variables, integrated, and the limits that we have taken for integration were 0 to V for V and 0 to t for t. Why 0 to V? Because the car has started from rest and now the present velocity is V. So, you get V is proportional to t raised to half.